Right. Good morning, afternoon. Today we have very excited topic. I did not put the contents on the slide, but we are getting to very interesting ideas and concepts. So there will be a block of 2 lectures regarding learning representations. So we are kind of trying to expand from the task of just classifying or regressing for some specific task to going towards weakly supervised, unsupervised, and towards learning more generic models which could be useful for multiple tasks. I would say like this roughly. Okay, so what is learning representations, or what kind of representations? In the nutshell, if you have some images and want to do something like classify these images, it would be good to have good features extracted from these images. So in the before the deep learning, there was a lot of engineering efforts to to kind of pre-process the images, extract something from these images, some features like, I don't know, thickness of the lines, some eccentricity, some fitted moments to the data in the images. And then if you have like good features, these measurements, then the classification becomes easy, so that the data will be easily separable in that representation space in these features, if you have these such good features. Now you have neural networks to do all the tasks, to do all the deep learning, including some intermediate liftings and some intermediate representations. And we've seen in the convolutional neural networks that, okay, they learn the first level representations, which are some kind of generic edge extractors and so on. That they learn some mid-term representations, which, even if the task was to, I don't know, recognize scenes, then the mid-level representations would be kind of informative about the objects in the scene and such. And now we want like to take better advantage of that, maybe to reuse these features for different tasks and to facilitate some properties of that representation of these learned features. So yeah, so on one hand, what we would like to have is some kind of represent every input data as maybe a vector in some space, so as a point in some space. And what we kind of then can express some properties that we like to do in this space. For example, we like to classify in this space or cluster the similar objects in that space. And now you recognize that to cluster these similar images in this space, it would be really nice if these points were like close together. So there must be some notion of a distance in this space. And if they are close together in that distance, so if they cluster together in terms of that distance, then our semantic clustering problem would be easier, because, okay, so the similar images, they go to the similar points in that space. Yeah, what else we would like from this stuff to be is that if we apply some transformations which on the images on the input data, which preserve the semantic meaning, like we change the style or the illumination or something, we would like these representations to be robust or ideally maybe invariant to all of the, the aspects that do not affect what we are interested in. So if yeah, so some like lighting and noise and other things. And we don't want like the coordinates of these feature representations to contain noises and some like redundant information which we are not interested in. But these two things are a little bit at contradiction, because it depends on the task what you consider important, which you then want to retain in this feature representation properties, or what you consider not important, and then it is a nuisance information that you would like to discard. So if you are maybe recognizing, so if you want to classify maybe cars versus, I don't know, people, then perhaps color of the car is not an important feature, and then you don't want to keep it. But for some other task, it can be an important feature if you want to do something specific. So in the end, it depends on the task what actually you consider as useful information, and what you consider as noise that you want to, and the transformations that you want to be invariant to. So if you want to recognize the pose of the camera relative to the object, then also the pose information becomes very important for you, and then you don't want to discard the in kind of some encoding of the shape and pose and the orientation in the image. So we have here like a bit of contradictory goals, and the hope is in practice that, okay, we kind of want to build such a representation that contains a lot of the relevant information for many useful tasks in which we are interested in, and discard like low-level pixel-level noise and this sort of things. Or a possible like a way out of this dichotomy is to sort of separate the representations. Okay, so we will just like somehow have some organized feature space in which these parts, okay, we don't know what if we are learning this, so we don't know which parts will be doing what, but we could sort of wish that there would be a space that part of the space contains like semantic information, some other part contains sort of maybe illumination and viewpoint information, some other part of the space contains maybe some low-level detail information, right? So all of the useful information would be there, but then kind of restructure it in a very different and much more convenient way, so that you could still easily do all of the tasks. Right, so that's the vicious and the researches towards getting a better and more generic and more useful features, and so it's now booming. Let's see like a couple of examples what we can do with these embeddings. So we discussed we can do classification, right? So then for this, if the features of the same class would be close together, then it's easy to do classification. We could do SVM or just basically any of the shelf classical model. If you machine learning model, if you apply on top of very good representations, then it's easier, right? So this would be like the approach for the much simpler fine-tuning and adjusting to a particular classification task than learning the whole network. What else? So we could do visual search, like retrieval. So here is example maybe from Georgos group to get an image, and having a database with the embeddings of all the images, you want to find out similar images. Right, and then the simplest variant would be to query with just the image and find the nearest neighbors in this space, and this would be your results. Okay, and then you may want to return not just the nearest neighbor, but maybe the top 10 nearest neighbors. But then at some point you realize, okay, actually, if these examples here are kind of densely represented in the data set, that you might want not to just retrieve all the the 10 images which have the closest distance to your current image in that space, but you kind of can walk through this graph and say, okay, so these are similar, these are similar, and these are similar, so that you might want then to retrieve the images which are further away, because there is a chain of closely allocated points in the graph. So you kind of can look at this graph distance in this space and retrieve based on that. So another example of like using this embedding, so these are also useful for interpretations, what this representation contains, and interpolating between the different representations. Okay, so here we are not interpolating in terms of generating the images, but we can look at this space and imagine some line in this space and then find the sort of points which are close to this line in this space, and then we could arrange them, arrange the corresponding images on a plot like this. So this is useful for organizing collections of images for designers, right? So that you see a full gradual spectrum from this flower to that flower with their features kind of gradually changing in that space. Yeah, so this is like the kind of properties that we like, so that the things which are similar, they are closer together, and then we can so then we can do some kind of vector arithmetics in this space, so that if you know some direction is making a flower red, then okay, maybe in that direction, if you apply it to some other flower, maybe it will also make that other flower red, and like things like that, right? So it's yeah, maybe I should add one more example for this to be more concrete. All right, now so this was like introductory part. What are these representations? What do we want from them, and what they are good for? And now we go into actually how we learn some representations. And I think the simplest example is word vectors. And so it's a kind of nice example, and we can connect it later on to what the generatively pre-trained language models are doing, what the contrastive learning methods are doing. So it is kind of starting point with no neural networks whatsoever, but it already contains many useful components. So the idea is that if you have some text like this, and if you look at some word, then the probability that some other words occur in that same sentence or not far away from this word, it is very different from the just like uniform random thing. It's pretty heavy-tailed and flat probability, so many words could be occurring together with some word, but not arbitrary, right? So the texts are not composed of just uniformly randomly generated words. So the texts are meaningful, and so what we can do is we can, for each word, we could set the problem to predict the words around it. And this is how it was done. So let's say we have a finite vocabulary of just n possible words, I don't know, 10,000, the most frequent words, or more if you like. So the words are going to be some kind of just discrete objects, right, in our vocabulary. And given one such discrete object, we want to predict the nearby objects. So how do we model such a conditional probability distribution to predict predict the other words. So this model is sort of arguably the simplest one, maybe. And the idea is that, okay, so for each word, we will represent it by some vector in this embedding space. Right, so you have this abstract embedding space, and here this point will mean like, I don't know what, man, no, what do you have in the text? Restaurant, perfect. Restaurant. And the position of this point is going to be learned, right? And so is for all of the 10,000 words. So we're going to have here exactly the number of points, as many as we have words. And the task is to allocate them in this space. So this allocation is not prescribed. And the model is that okay, so what is yeah, let's see. So here this task was a little bit asymmetric because we have this kind of observed word, and we are predicting the words in the context around it. And they used two such embeddings. So one embedding was for this green word, the one that we condition upon, and the other embedding was for the other words around. So, right, so let's say this is our green embedding, and what we want is that the things in the context which are embedded, so this is our u of x and v of x, and this is our u of y. So this embedding there are two embeddings because of the asymmetry of the problem. And given these two embeddings, so what we want is that this vector signs up some similar or close together. So actually, how do we phrase the learning problem is it's saying, okay, we will compute such scores, which will be scalar products between this embedding and other word embedding. So and if the other one is far away, so then this score will be, the scalar product will be high. And okay, so if it is orthogonal or far away, the scalar product will be low, and if it's close together, the scalar product will be high. Okay, good. And then we define this predictive model to be this sort of softmax model on such computed scores, right? So it's this soft, if you like, of this v of x u of y. Right, so that's it basically. So then the softmax, yeah, you have the formula in the slide. We want to classify. Okay, we want to predict the words in the context. We want to predict the y, and we assign the probabilities to each such possible y according to this score. And then the true words, we observe them from the text. And this is what we substitute in this formula and evaluate the likelihood of this given text under this model, and then we can maximize this. So this models, theoretically, it learns to generate the models in the context of around of our world based on this pairwise similarities, right? But now the twist is that we are not going really to use it for generating words around the current word. So this is not a very useful task on its own. But what is useful is this embeddings that we learned. Yes, and then yeah.
I don't see why it doesn't collapse to single point, because that would be like optimizing.
No, because of the normalization.
The normalization goes over all words.
Yeah, it's over the whole vocabulary. So in principle, all of the other words serve as kind of negative examples in this context. So okay. Now the vectors, the embeddings that you learn, they found, they discovered they actually satisfy some very nice properties, and there is some arithmetics on this on the vectors representing particular words. So here are some examples. So the direction between two words appear to capture some relations. For example, if you take the word vector for the Czech Republic and the word vector for Prague, so if you kind of subtract these two vectors and add this to the vector France, so then we will find that there is an embedding for Paris very, very close to the result. Yeah, so these are, okay, so examples like the king minus man plus woman gives approximately the same embedding as where the queen is, and these capitals of cities, or the Czech plus currency is approximately the embedding of the koruna. It captures this semantic relations, so it also captures some syntactic relations, like the quick minus quickly is about the same as slow minus slowly. And what is not illustrated here, maybe also like a similar words and concepts, they cluster it together in this space. So this is the kind of embeddings that we want, and for some time these word vectors, they were used then as a starting point for like more concrete downstream tasks. So suppose you want to do some question answering or some analysis. So yeah.
Is there some explanation as to how like this semantic and syntactic like meaning is encoded when all we're doing is kind of like looking at words that appear close together, especially like the part with the vector arithmetic, the fact that works is kind of surprising to me based on the learning task formulation.
Why this behavior occurs?
Yeah.
From the fact that we want to generate nearby words. No, from this design that the probability distribution to predict the words is proportional to the exponent of this sort of scalar product, which represents similarity, which represents, in some sense, orientations of these vectors. So in the context of the restaurant, the related things occurring. So this should then have high scalar product. So okay, this could explain maybe kind of co-occurrences and grouping. Maybe it does not directly explain why these differences are the same.
More something about like inherent structure of language that's maybe captured like to achieve this.
Could I ask, is there some analysis, is in the term which is used for the computation of the assay loss function on the previous slide, is the size of the
The lens.
large magnitude.
Oh, right. Yeah. No, it's so here it's not, I believe, so it's learned, right? So so we pose it as multi-class classification problem that the red word must be preferred, must have high probability over the all possible words in our dictionary. And the softmax is normalized in that sense because you have all the possible alternatives. And the sharpness of this prediction, so how confident we are to predict a particular word, I think this would depend on the lenses, on the scales of these vectors. But then it will be learned from the data because if so, this model it cannot predict very accurately. It is not possible for any model to predict accurately what should be around one single given word. So I guess these scales will not go to the infinity or something. So they will. Could you say again? Softmax? No, it's if you mean the scale of these vectors v or u, then it is not invariant to the scale. So it will be sharpening, right? So if you multiply here and here, then it will tend to be like a delta distribution predicting only one word out of everything.
A very quick remark, I think that's not necessarily what we want for them to all be unit scale because that allows to capture like basically priors about how often the words appear generally like in a text, which is like for this task, if the word and will appear in very many sentences as opposed to some other words. So,
yeah, so here it's not desirable indeed to fix the norms of this weight. So they are learned such that the scalar products of the corresponding scale to represent correctly the uncertainty, represent these probabilities and frequency of these co-occurrences. All right. Now I would like to kind of speculate about how this relates to the generally pre-trained language models. So what we did, we took all the words and then we learned some embeddings for all these words. Now, do the GPT models learn embeddings? Do they train in a similar way? And it is yes, but a little bit differently. So this diagram is to be read from bottom to top. So this is how the processing would work. If you have some text, so currently this is not discretized into words in the vocabulary, but it's chunked into like smaller pieces. Here is one example of such chunking. It's called tokenization. So each chunk is called a token, and so we are kind of chunking the text in these tokens. And I think the recent tendency was that so before they were making these tokens quite large because then the words that have similar roots, they could be somehow understood by the model, so it was better. But I think recently they are shifting to kind of shorter chunks to make it more general, so it would cover all the languages within one model at once, and all of the existing or non-existing word combinations. Anyway, so we have this tokenization on the level of the pieces of the words, and then for each token there is the embedding vector learned. All right, so it is an embedding vector per token. Maybe that's not necessarily represents some semantics of if it is so if some combination of letters which is frequent, maybe it doesn't have semantic at that point. But yeah, if we input one word to the GPT to the language model, and do some processing on it. At some level, we can extract the feature representation, which does capture maybe the semantics of that word. And then in the GPT language models, these embeddings, then they are processed somehow by some self-attention and whatnot, multi-layer perceptrons. And the result of this processing is again like a new layer of the representation. So kind of different embedding for each token. And this goes, multiple layers of that is used. And on top of that, we're gonna predict, so this model here, if it inputs these tokens from 1 to 4, it's gonna predict the token number 5. So it predicts ahead. And by design, it is also, at the same time, it is also trying to predict the token 4 from all the preceding tokens and the token 3 from the tokens 1 and 2, and maybe even token 2 just from the token 1. So here the connectivity is in such a way that the information that goes in this node to predict the token 3, it cannot be based on all of the future tokens. So only the information from this T1 and T2 can propagate here. And therefore, this classification layer has such connectivity, but also all of the below layers, all of the self-attention layers, they must also have such a connectivity to follow this causality, so that it's not allowed to use the information from the future tokens from T3, T4, T5 to construct the representation here, right? So we are building kind of deep representations, but causal, respecting the causality. And therefore, I mean, at this point, the T2 is representing maybe the words before. So it is now context dependent, but the context only to the past. So this representation somehow describes the part of the text before the T2. Was it a complete word or not? So it's until T2. So if you input one word and maybe look at the last token in this representation, then we are getting some kind of the representation of a word on that particular level. And it would be interesting, I have not created such an example, to look at these representations, how they have maybe for same notion in different languages, whether they are close together and this kind of things. I think it would be interesting to look at. Anyway, so they are trained also to classify out of all possible tokens the one that is actually in the text, right? And the loss function consists of this sum of the likelihoods of all of these predictions, because in one pass we could predict the next token from all of the preceding ones. So it is kind of more learning information, more efficient training. But you see, it's sort of, again, similar prediction task for the purpose of generating text. Only now this time we can actually really use it for generating text, and then this is useful for many things. Because having the story so far, the model could continue, and it could continue to the level that it could answer the questions, reason, and okay, you know. Anything to add here? Maybe. Vocabulary is still finite. So if you chunk it into the letters, then you need not so much, right? It's maybe 30 letters per language plus different funny Unicode symbols, and then it's not too many. So they are making it a bit more. I think around 10,000 tokens or more. But that still covers all the things they find in the text somehow.
Maybe I would weaken your
I don't know how many characters in the chain is. Does anyone know?
But like the Llama multi-language is 131,000 tokens in the whole vocabulary. And that's including like the special unused tokens that you can use for downstream.
I see. Okay. Okay. Yeah. So my is very broad ballpark, but it seemed to me that recently they were shifting to shorter tokens.
Like the older models with multi-language vocabulary is like 250,000 or 300,000.
I see.
And they don't do that anymore. It's like 50 for English and 130 for multi-language nowadays.
How many? How much? How many?
50,000 for English only models and 130,000 for the multi-language.
Yeah. So okay. So I did not have the accurate info on that.
maybe just like on its own, this model still can't reason and do all the stuff we see. And it's just a good representation which you can then use, and you still have to do some training on top of it to get what you see today. But it's just a good representation.
Oh, you mean if you train it generatively out of the box? Yeah, they are.
Just bubble words, yeah, like without any like ability to answer questions and stuff like that.
Yeah, then that's then the LLM magic stuff.
It's like reinforcement learning, but we're talking about representations, and this is a cool representation.
Yeah, so then there is this part which is the reinforcement learning, and the other magic stuff that how could it actually do very useful and reasonable things. And I mean, so this is the principle for pre-training the features, and it's quite plain, right? You just do this simple prediction of what is going to be in the text. You have a rather plain architecture, so with this self-attention and the MLPs, and you scale it a lot, you scale the data a lot, and then it's crazy that it is having like really amazing representations to do something, and then with some additional fine-tuning that it is then they were doing some questionnaires like, do you think that language models are smarter than dogs? And then people are answering, in some sense yes, but in some sense no, because they don't have like the dog's emotions or something that the dogs can do. Some other things I forgot. And then somebody writes a comment, man, these models are smarter than most of the humans. What are you talking about? Anyway.
Very quick question. Is
Sure.
causal attention still like widely used in the language models, like only causal? Because I've been looking into vision transformers, and their like global self-attention is used like over all image batches.
It depends on the task. If you are predicting the next word, then you kind of have to use it. If you look into that, then there is a simple
but
solution.
like for all neurons, even like not just like the last kind of predicted token, because for the previous one, if you have some sort of context window, you could like potentially look at multi. Okay, no, never mind.
You're always looking at
it makes sense. It makes sense.
You cannot look at yourself because
Yes.
I mean in the inference you cannot do it because you don't have it, and in training then there is a simple solution, just say that.
Makes sense. I agree with that.
Okay, it depends on the task.
Yeah, to me the question is like, what do you do with it at the inference? So in the inference, obviously you don't need this top layer, so you discard this. But then this one is needed because it is some representation of this T1. Also, maybe deep representation, but without any context, right? So then you cannot discard anything else. So all other representations are used in here through this connectivity graph. In vision,
It's a different task because you have the whole image
there
at once.
were also like at some point it was popular to do like total regressive things with vision, where you were trying to generate images in this kind of fashion that you are like generating one pixel at a time or something, or
like some block by block generating.
Like this.
Yeah, then it could be.
Train something, it worked kind of fine at some point, but then yeah, people found other things that generate images better. So.
And likewise for the language models, before there was BERT, and the BERT did not have the casual self-attention, but it was doing concrete tasks, so it was not learning this generatively pre-trained for learning representations. It was solving, let's say, translation problems. So input text, output. So you see the whole sentence to translate, right? Before you, and you could do whatever with all the words in that sentence. Just give me the right translation. And you can still kind of take this learned representation, which are trained autoregressively, and fine-tune them non-autoregressively, I guess. I don't know if anybody was doing that. So let's go. So it's an exciting topic, but it's like was not the main thing for today. Yeah. Anything else? No, it's great. We like to have discussion. It's making it more interesting. Now, let's go further. Okay, so how do we facilitate more useful properties of these learned representations? Besides that, we say, okay, we're just gonna learn to predict something that is part of the data, but which we do not give to the model on the input. And there is like a direction of research called similarity learning or metric learning or contrastive learning. And in this direction, we kind of say more concretely what do we want from these embeddings in terms of what should be close together, what should be further away apart. And we set up the training in such a way that we find the examples which should be similar, and then the examples which are dissimilar, and then we learn based on that. I think this slide is kind of general introductory slide. So they're saying that there is two flavors where there is supervised learning, where actually for an image, let's say this is some dog, you have some positive examples. So let's say the images of some other dogs, and you assume to have some negative examples, which are some images of not a dog, right? And the self-supervised flavor of this is that, okay, so you have some image and you don't have positive examples. So nobody told you the class label, so nobody have provided you with examples of the other semantically similar things. And what you do instead is you kind of just generate from this image many different augmentations. So it is still the same image, maybe with change in illumination, change in contrast, rotated, or maybe with some part missing. And what you want is that all these variants, all these like harsh augmentations of this image would be still close together in this embedding space. So this embedding space is here depicted as a sphere for the reason of normalization, and we will come to that a bit later. And so you want like here all these self-generated examples which you created from the same image, but which you believe preserve the kind of semantic content of the image to be still close together. And then you take all of the other possible images that you have as negative examples, and you say this must be further away than these ones, even if the other ones contain some dogs. You know, it's gonna be most likely probably not very often. So on average, you will learn so that all these transformed things will be somehow grouped together, and then you're hoping to achieve the properties that, okay, your representation will be more invariant to the different transforms, and then the semantically relevant things will group together. Now, let's address this question from the point of view. Okay, we have this space, and one component is this vector, so the embedding of an image, the one component of this representation, and the other component of this representation is actually how do we model the similarity between these two embeddings in this space. And it's maybe not obvious, right? So, okay, so one maybe proposal would be, so if you have some input image and some other input image, and we want to learn similarity, right? Then we could like build some neural network that is taking these two representations and then processing them, and it outputs similarity. The other approach, but okay, this maybe will not be very efficient for retrieval because we will need to execute. So this similarity is kind of computationally expensive. We need to execute this neural network that takes two inputs. Another approach, like to make, instead of this neural network, to make a very light operation, for example, just scalar product of the features. So we just have like maybe longer feature representations for the both images independently, and then to compute the similarity, we just compute the scalar product. Yeah, so you could see there is some trade-off maybe that this one is maybe more general. It could learn some more general similarities. But we might have problems like ensuring if you like to have triangle inequality or some good properties of the similarity. So this is not like given from granted. So we might need to take care of that. And it is more complex to compute. So also it is more flexible. So it could learn something more, but it's then more computationally expensive. Whereas this one is simpler and by design respects some good properties. And it makes our feature space interpretable in terms of this scalar product. Okay, so we know what is far and what is close in this space in terms of this Euclidean geometry. So the scalar product is also related to the Euclidean distance, you will see. And in fact, it is known that if you have any kernel, so which means like positive semi-definite sort of metric on any inputs x and y, it is possible to represent it as a scalar product of two liftings. Only there is a catch that these liftings must go sometimes to very high dimensional space, and for some specific kernels even to infinite dimensional space to represent that exactly. But nevertheless, from this point of view, this architecture is still general enough, right? So by learning a good feature representation with high enough dimensionality, we are not losing generality in saying that, okay, we're going to just measure similarity by this scalar product. Because it is general, so it can represent everything we need. And we hope that the architecture is good enough and that the feature dimensionality is high enough so it can do this. And it can, for many tasks, it can do quite a lot.
Theoretically, like the representative power of the first is still higher, right? Because in some cases, the dot product of like the lifted features can be finite, whereas the lifted features themselves.
Yeah. If you limit the dimensionality of this, then this becomes more general. That's true. Yeah. All right. So suppose we settle on this and we decide to use scalar product. We can also know that there is the following relations to the other options. So the other options would be what is kind of natural to consider in this space is just distance between these two vectors, right? Euclidean distance. Or the other variant is the normalized scalar product. We just take scalar product and divide it by the norms of these two vectors. And all these variants have been used, and they have slightly different properties. So this scalar product is kind of more flexible, but it does not obey triangle inequality. So it is not as good for retrieval. The retrieval becomes more complex algorithms for nearest neighbor search. If it is the Euclidean distance, the nearest neighbor search is faster. If it is this correlation metric, there is also correlation nearest neighbor search, it's also fast. However, what we can note is that all of these three things, they become identical if we normalize the vectors. So if these norms by design are set to be unit norms, then the correlation is the same as the scalar product. And okay, so the Euclidean distance, so the distance is large if the vectors are dissimilar. So we take similarity, we define as the negative distance, right? So if we expand this negative Euclidean distance, what we get is so what do we get? So we obviously got this, and if these are like unit vectors, then they affect just up to a constant, this similarity. So there is equivalence between the Euclidean and the scalar product also. And then everything is very convenient. So this has been kind of established common design to take this similarity to be just the scalar product, and to have the neural network to produce normalized features, like to include the normalization on the output. And hence, the embedding is on this hypersphere of the unit norm representing vectors just by design of the network, right? Yeah, okay. It was even a special slide including the normalization here and showing that, okay, so now this representation is going to live on the network. Now, recently, I don't know, has somebody been to the colloquium the last week? No? Now, recently, people were arguing that okay, this embeddings is actually not sufficient, and for some things it is not very good to represent it with the scalar product, because maybe it is possible to represent what we want with scalar products, but it would take much higher dimension than otherwise. And now what is the alternative? So what are the options? And the one option is called hyperbolic geometry. And this is what we're going to do is that we want to define a different distance in this embedding space. Instead of the Euclidean or instead of this scalar product. And we will do this in two steps. So first we will define this distance using this hyperbolic geometry, and then we will discuss how it could be useful. Right, and then to define it, what they usually do, they plot you or draw you this hyperbola, 1D or 2D, and they will tell you, okay, so now our embedding space is this manifold of these points on hyperbola. So instead of the sphere as we had before, now the points must live on this, and the distance is something. So the distance is this formula, right? So the hyperbolic cosine of this Lorentz inner product. So do you have some formula for the distance? Okay, how to understand this, what it is doing? So one thing we could just, so first, because the point must live on this hyperbola, we kind of need to project this point somehow on the hyperbola to have it in the first place. And maybe if initially we have some representation x here, so just unconstrained representation, like coming out of a neural network, we could sort of construct the additional coordinate according to this plot, and this will be our point on this hyperbola. But then, what does it mean, the distance on this in this hyperbolic manifold between 2 points, like this x point and y point? It is not the sort of Euclidean distance along this manifold. No, no, no. It's not like with the, you know, sometimes manifolds are defined by embedding them in the Euclidean space. So you draw a sphere and you say, okay, the distance between points is the length of this arc because it was the metric in the space in which it is embedded. So this is not the case here. There is this hyperbola. It is the manifold, but it has a different metric. So the distance between these two does not have nothing to do with this graph. So the distance is given by a different formula, which you don't see in this graph. And what we can do, we can just kind of plot what this distance looks if we are considering just this projection, this slide. And it looks like this. So then if you look at the center, then the circle of points away at radius 2 is this. If you are looking at distances around some other point, then this is sort of the contour line of all points with the distance 2. If it's further away, then it's more elongated. And what you observe here is that this sublevel set of the distance function, it's elliptic in this space. And then the further away you are from the center is kind of more stretched and more stretched. And now what we can do with that is maybe, okay, yes, so we have this space and we have this distance function which we can visualize, but why it is stretched like along the radius? Wouldn't it be equivalent if we could kind of just compress the whole space and then make it not stretched? Because if we compress the space, maybe this distance will become simpler, right? So why this stretching is again a little bit arbitrary. I mean, we can non-linearly stretch this space and reparameterize this distance function, and it will be maybe not ellipses but some other curves, but even more elongated or less elongated. So this is also like still arbitrary. What we can do is to try to compress this space in such a way that these ellipses become circles, and that's called the Poincare projection. So we took all this stuff and kind of contracted to a radius, to a disk of radius 1 by this projection. So we take x and divide it by this 1 plus the something dependent on the norm of the x, and compare it to the projection on the hypersphere where we've been dividing by the norm, right? So here we are now dividing by the norm kind of plus some constant, and it makes it, instead of getting a point on the hypersphere, you are getting the point inside, right, of a ball or of a disk. Okay, and now in this disk, these distance maps look circular for any point. But the difference from the Euclidean metric is in that if you go away from the center, then the radius becomes smaller. So this point has the neighbors with distance closer than 2 in this circle or ball, this point in the smaller ball. So this kind of has this property. So okay, what is this function is doing? It is still a distance, so it is 0 if and only if points coincide. It is symmetric. It satisfies triangle inequality. And it has this interesting property that the points closer to center, they have kind of larger neighborhoods with respect to this distance. And what is good about this is that it is appears to be suitable for capturing hierarchical relations. So if you suppose you have something like this, you have some general word like animal, then you have something more specific like dog, then you have some maybe what's that, puddle, or so there will be many dogs, many animals, and the further you go through this hierarchy, the more sort of refined and the more instances there could be. But a puddle is still an animal, so you want these two to be close in the sense, and that if this is like, okay, so my dog and particular image of that dog. So you want still this stuff to be similar to the general concepts in the hierarchy that are relevant for that. And it appears that this distance could do this. How? So basically, the concepts which are more generic will be closer to the center, and then they are similar to lots of the space. And the concepts which are further away, that they would be less generic, and then they would be similar to less things, but they are still kind of more similar to the things towards the center. So they are more similar to the things which are more capturing more generic concepts. So in principle, if we endow our representation space with such a metric, we might expect that it will learn to allocate the concepts according to somehow respecting the generality of the things. There is maybe some caveat to that, is that there could be more general concepts which are fit in this. So they could be, some text label that says how cute or something like this, and this will be also general, and it will also should be close to the poodle and everything, but maybe not necessarily it must be close to the animal. So the reality is more complicated, right? So not everything is purely hierarchical like this. So some things would be maybe harder and not possible to capture in this space, but some things can. And they show that, okay, to represent such hierarchical, so if you take this graph, you might want to say that the similarity should be proportional to the distance in this graph. Like similarity between the picture of this dog and the word dog should be 3, to the animal maybe 4, and like proportional to the path in this hierarchical graph between the two words. And they did an experiment to represent it with the Euclidean embedding or with this hyperbolic embedding. And the hyperbolic was much better in terms that you needed much fewer dimensions to capture these graph distances. And while it is still true that we can represent even this hyperbolic distance using some lifting and some common scalar product, it is still the practical aspect of that. Okay, you might need a higher dimension for the lifting to do that. Yeah, so this is like on the edge of the research to think of these hyperbolic geometries which facilitate hierarchical representations and put them in the learned representations and maybe in some other places. Any comments or questions about this? So by the way, these illustrations, they kind of did not exist. I had to create them, consult in the ChatGPT. And then it was, okay, now it's more clear than when, and okay, so this also I've created. So what they have in the paper, it was not intuitive for me why it somehow corresponds to the hierarchy. I hope it was telling to you something.
The images are great, like I got the idea.
Mm. Okay, cool. Now, okay, yeah, so we discussed what? We discussed how we design the embeddings and how we design the metric. And what we now also, the two topics are remaining is to discuss triplet losses. And there is a nice point that like all of these triplet losses are somehow related to this classification, either with categorical classification or the binary classification. And one more topic remaining to discuss, like this visual language models. So combine the embeddings from the images and from the text in the same space for them to be related. Okay, so here quite briefly. So in this instance classification problem where we said we kind of create artificial examples of the same image, we can formulate it simply the learning. So we can simply formulate the learning in the way that, okay, so for the instance, we would create a transform, which would be like a random transform of our image, and we consider it as a positive example. And then we create these scores, so it will be a scalar product. So now forget about hyperbolic, so now we will do with scalar products, everything back again. So this will be the score for the transformed image, and then we can compute the scores for all other possible images. And what we want is that we build such a softmax model on these scores, and what we want is that we want to predict whether, like, out of all possible negatives and the truly transformed instance, we want the classifier to pick the truly transformed instance, right? So this is like multi-class formulation. So we set up such a supervised learning problem, in fact. So we call it the self-supervised, but as a learning principle, it is supervised. So we create an artificial transform, and we know it must be this very instance. And we ask the model to, if the model does not know whether that we generated this positive example artificially, the model must select out of all the possible negative examples and this positive. It must predict that this one is the one that is corresponding to the image, according to this softmax model. And then we take the log likelihood and train that as a kind of classifier, if you like. Okay. And similarly, other approach is the following. So this like a well-established and well-known concept of triplet loss. There is, in fact, a family of triplet losses, or contrastive losses, if you like. And it is designed more explicitly. So before I was saying, okay, we set up such a classification problem and doing this. Now this approach is seemingly different in that it says we're gonna specify directly what do we want from these embeddings and what we want. So we assume on the input we have some positive pairs that somebody labeled for us, so which things are considered relevant, and some negative pairs, which things are considered not relevant. And in particular, the relevant things could be of the same class if we had the label data in the first place. But we are not going to train it as a classifier to predict the labels. We are going to train it in the way that the things which are similar should be closer together. And so we look at these distances between some anchor point and all our other points. And what we want to say is that the example which must form a positive pair with this anchor, it must be closer than all the examples which are marked negative, right? And hence this is like a triplet loss, so it involves this anchor, a positive example, and a negative example. And if this distance to the positive, denoted dp here, is smaller than the distance to some particular negative, then we are fine. Then we are saying that, yeah, okay, so that's correct arrangement, and we don't want to penalize this. So let's draw this distance positive minus distance negative. So if the positive is smaller than the negative, then we are here, right? So then we say, okay, we don't penalize, so it's okay. That's fine. And if this becomes larger than 0, that means the distance to the positive example becomes larger than some negative, for example, in this case, then this is something that we don't want, and when we will be querying with the example A, we will find the nearest neighbor as this negative example, which is bad, so we would want to retrieve this positive. So it must be closer than this one, right? So then we're going to penalize, and we're going to penalize proportionally to like how much this is violated. So, okay, so we put some hinge loss here. Right, so we kind of put this hinge loss on this difference of distances. And then technically we have two options. Either sum these hinges over all negative examples, or to consider the worst case. So, okay, let's find the negative example which is violating this requirement the most. So in this case, this one, and then penalize only this the hinge associated to the most violating negative. So respectively, we obtain these two variants of this loss function. So one is summing, and the other is taking maximum over all negatives. Now I think, okay, so we will have a lab in which we will practice these triplet losses, I suppose. And we will have a seminar also in which we will work a little bit more with these triplet losses. And today, I think I would like to emphasize the following. So these triplet losses, they are actually very related and very similar to this classification and generatively pre-trained formulations that we've discussed before in the following way. So if instead of this...
Mm-hmm. And you measure it by having the same label, yeah? But then, of course, if there is like similar lighting or similar poles or similar stuff like that, then you don't capture by this, and you sort of like take the representation where you ignore all this, probably. Is it used also in the situations where you want to capture like this bigger variety of stuff or not?
Well, may I answer from my technical side first? Here it is assumed that how you define what is similar and what not is external to this formulation, right? Maybe a user clicks which pairs are similar and not similar. Maybe it comes from some known labels, maybe from somewhere else. So here it's assumed that you have this input in this format, that some examples labeled similar and some are dissimilar. And then depending on how you set up the learning formulation, how do you mine this data, then it could be the self-supervised or supervised or something else.
Yes, but I haven't seen it used much with like general, for it to work well, you need this hard negative mining. You have to do it kind of often, which means like that you find the pairs where the negative is actually the hard one and stuff like that. And I think in self-supervised people just they went like, okay, if you have just a large batch, then the other thing with the like, classification thing already works, and this is.
Okay, I just wanted to say this is my own critique of this, like the class table is not sufficient, and that's why we are using other representation. Still, Shekhovtsov is like it's general, so it could be used in this way. We don't do it very often because it needs this external signal, which is often difficult to collect. I'm just like wanted to say these things, but still, it's like in general, nice technique. I'm just like having this little issue with this.
I want to say. I want to say today the following important message. If you smooth this hinge a little bit, then it becomes the same as these classification variants. And mathematically, what it means to smooth a little bit. Would you kindly close? What it means to smooth a little bit. So instead of maximum, we can consider the function called smooth maximum. And it's defined as follows. So for two variables, it is the logarithm of the exponents of the arguments. And we could control how much it is smooth. So either like this or like this by dividing by this hyperparameter inside and multiplying by it outside. And okay, you could also interpret it as we take maximum, and instead of considering the arguments of the maximum, we perturb these arguments with a little bit of noise, and then we look at what the maximum will be on average. So this is also like a useful latent variable representation of that, but that's not so important for us at the moment. What is important is that instead of now the maximum, we are getting the like logarithm. So if it was the hinge variant with the sum over all of the negatives, where was a maximum of 0 and this difference between positive and negative, then if we are smoothing that variant, we are getting the this formula, so which is the log likelihood in the logistic regression model, right? So the logistic regression model has the predictive probability okay, now I need to say what? Okay, so that these examples are similar given the distances. And it is the sigmoid function. So 1 plus e to the difference between these distances, right? So we can sort of approach this learning problem in two ways. So either we consider a pair of positive and negative for a given anchor and saying, okay, so this must be classified as 1 and pose it as a binary classification problem and some overall possible negative examples of these likelihoods. Or we could say that we are summing all of the hinges in this triplet loss and add a little bit of smoothness to the maximum. So that becomes the same. And if we apply this smoothness to the other variant, which is like the hard negative case, the maximum over the negatives, we recover the softmax loss. again, with this, maybe what I'm missing here is these temperature hyperparameters, right? So that the smoothness here should be controlled by this temperature. So we should, here we got some temperature, and for the softmax we should also get some temperature. Yeah, so maybe the details are not important. The intuition is that, yes, so there is this model with the hinges, which is called the triplet loss, and there could be two variants. But in fact, if we add a little bit of right smoothing, we are obtaining the other popular training models and training objectives, which are either this binary or the categorical loss formulations. And one example of such categorical loss formulation with these temperatures here is contrastive language image pre-training, or it is used in the contrastive language image pre-training. So this, I mean, this could be used for any triplet loss objective, for the self-supervised learning, for images alone or supervised. But let me now kind of illustrate two things together, this text and image together, and the use of these losses in the training. All right, so what we're gonna do is we're gonna have the labeled images. So there is an image and some text description of the images, of which there would be maybe a lot on the internet, or somebody could label this in a natural way, that describing what is in the image. And there would be multiple labels even for the same images. And we can encode separately. So we can separately, we are preparing an encoder for the images. We're going to learn the encoder for the images. For the text, we could either maybe start from a pre-trained encoder for the text and fine-tune it, or do something else. So not important. So maybe even freeze the text encoder and have like the last layers of it only to be adjustable for the embedding that we want to learn. So something must be learnable in this encoder, so that it would put the embeddings of the text in the space that we want. I think no.
There were cases when it's fully frozen, and you just train the image.
So you train the images to map to the language space. Ah, okay, could be. And then, so suppose you have like a batch of these images and a batch of the texts for the images. And then you know that the image I1 must correspond to the text T1. So this is, you have it in the data. But you have also all other text descriptions, which are from the other images. And then what you know at this point is that you want actually the image I1 to be close to the text embedding of T1 and far away from other text embeddings. And this is the case for your triplet loss. You could say, okay, I want this pair to be, so this T1 is a positive example for this anchor, and all other text are the negative examples of that network. In the reformulating this in terms of classification, you are saying, okay, out of these n texts, I want to predict which one is corresponding to the image A1, right? So, and so I set up multi-class classification problem. So there is this n options, and my multi-class classifier must select T1, and the scores are given by the scalar product between features of the images and the text labels. And here, because these embeddings, they are normalized, right? So the hypersphere, they cannot learn the scale. So and in this context, it is important to set or learn this hyperparameter that somehow adjusts the scales of the for the score, so which controls how sharp these predictions are, so how deterministic or broad they are. Okay, so we did it like for one image and all the text pairs. So we could do it for every image and all the text pairs, and we could do it symmetrically also for every text and all of the images. So hence there is this symmetrized objective, and that learning that allows us to kind of put images and the text in the same space, and that opens very, very many options, right? So we could label, so we could classify the text in the kind of open vocabulary set, and we could classify images or we could search for relative images with the text queries and so things like that. Okay, so maybe last bit to that. Now we've discussed essentially there was two variants of what to do with these hinges. So that you could sum them or you could take the maximum, and this was corresponding after the smoothinizer to this categorical or the binary classification setup. And yes, why not to use this binary classification setup also for training the language image models? And so somebody did, and what is the setting? So actually, if image I is paired with the text J, then we give it a binary label of 1. If they are not paired, so if it's some random pair of image and the text, so they are not corresponding, we give it a label of -1. It's convenient for the logistic regression model. And we set up our predictive model to predict that it is the corresponding pair based on these embeddings of I and T as just this logistic model, logistic classification model, and set up the loss as the sum over all of the positive examples and the sum over all of the kind of all examples, including, so I is this sort of our average over the data set of some examples, and J goes over again over the same data set of all other possible text representations. Now that in practice, that means we are doing these sums over some batch. And for some pairs, we have this label Z that they are matching, and then the likelihood is for the matching pair. But for most of them, the likelihood is for the non-matching pair. So to compensate for this imbalance, they add in here like a little bit of the bias to this color product and initialize this to some value that initially compensates this imbalance. And then this is important to achieve the learning in practice. But from the conceptual point of view, what we are doing here is that we are working with this smoothed variant of this loss, where we had sum over all of the negative examples. And it works. So what they show, yes, it works also the same or maybe better in some cases. And maybe it works better with a smaller batch size, or maybe it is easier to compute in a distributed fashion. In some cases, if you have this double sum, it's easier for the stochastic gradient descent algorithms. You don't need to deal with the fact that, okay, so here, if you wanted to consider this classification out of many negative examples, and if you wanted to consider this the worst violating negative example, so this hard maximum or this soft maximum, then you would need to have a large batch size, right, to find this negative example, which gives you a non-zero gradient. If you don't have a large batch size, then you are actually you are making a stochastic estimate of something, but not of the initial learning objective that you wanted, not of the maximum or not of the soft maximum over all possible other images. So you are changing the problem formulation, and maybe depending on the batch size, you can get very different performance. So here, at least theoretically, with this sigmoid thing, you are not dependent on that. It is a double sum. You could just sample a random pair of text and image and put it into the loss and just have a batch size of 1, right? In practice, it's not the case. That is, they still need some large batch size to achieve good performance. This I don't know why. Maybe it's the training efficiency, like how stochastic this gradient is. So probably in practice you can also, if you have the parallel devices, you want to run to utilize all of your computation power. So you don't really want to make steps with batch size 1. You do want to make steps with large batch size, or you will have. So if you are using very small batch size, you will be making maybe small steps, but in time it will take as much as you would be computing on the parallel hardware. But you will have to make smaller steps to compensate for stochasticity. So it's kind of, in practice, if you have a lot of this parallelism, it's still good to use large batch sizes. But here now, maybe it is, I don't know. So it is as sensitive to this batch size as the softmax. And anyway, at least in principle, it is like equivalently good solution, or maybe even somewhat better solution to the problem. Right, and I'm over time, so there is some summary takeaway. Yeah, so we have considered this family of triplet losses controlled with smoothness controlled by hyperparameter tau, and seen that they are equivalent to this classification likelihood losses, and we discussed these different variants of embeddings and how they're useful. So to what is worth saying, that if you are interested in other methods for learning representations, like there are these autoencoders, masked autoencoders, different bootstrapping variants, many of them are covered in the MPV course, and maybe the lectures were recently already. Yeah, but there are recordings also. And for our course, we will go to, so we discussed generatively pre-trained text models, and we discussed sort of learning representations in terms of this metric learning for the images. In the next lecture, what we're gonna do, we're gonna discuss like generative training of image models, and specifically relational autoencoders. Okay, that's all.